I'd like to introduce our presenter, Nick Sischka, who will discuss lens performance curves. Nick is a senior vision solutions engineer at Edmund Optics. He specializes in optics for vision systems and supports imaging and machine vision customers with application knowledge and design assistance for modification or customization requirements. He has also successfully trained EO's global vision partner on the specifics of how optics interface with cameras and lighting. So without further ado, I'd like to turn it over to Nick.
Thank you so much for the introduction. I'm really excited to be here today to talk to you guys about lens performance curves and how to choose the right machine vision lens for any given application using some more advanced topics. First, I'd like to thank everyone who is sticking around from part one and to welcome and thank all of you guys for joining us for part two. We're going to dive right in. We are going to do a very quick recap for what we went over in part one just to get us all on the same page, make sure we're all talking about the same verbiage. For that recap, part one really covered the practical implications about choosing a machine vision lens. We went over how to use an imaging calculator to get you started and get along the right track for what type of lens you should be using for any given application. We also talked about some of the pitfalls that can arise when using a machine vision calculator or lens calculator, and some of the things that can arise with issues with performance or too many options to select, and that can create issues when you go to actually purchase a lens. What we're going to cover here is how to take all that information and look at spec sheets and look at individual performance data from lenses to choose what's going to be best and how to maximize that performance. Specifically, what we're going to be covering today are lens performance curves. We're going to dive into a lot of detail with the individual curves. We're going to cover several different types of curves, and we're going to cover a lot of different things today with those. Primarily, we're going to focus on three different curves, which we're going to get into in a minute. We're going to talk about those different types. We're going to talk about how to read them. There's a lot of information on these curves. They tend to be really information dense. There's a lot of information that's put on a spec sheet for a specific lens, and they have to be information dense because lenses can be used all across the board. They can be used over a variety of working distances. They can be used at a variety of different apertures and wavelengths. And so there's a lot of information that are on these curves and on the spec sheets, and we want to be able to break those down into a digestible way to be able to look at these curves and know what you're seeing. We really want to tie that together with some real-world examples to say it's fine to look at a curve on a piece of paper or on a spec sheet on your computer, but actually seeing what that would translate to in a real-world scenario is really important so you know what you're actually going to be getting from a lens when you purchase it. And lastly, we're going to wrap up with some design trade-offs in terms of things like resolution and distortion. We're going to talk about how lenses are designed for specific areas and use cases and how lens performance curves can help you determine where a lens is designed for. So firstly, what are lens performance curves? If you look up any lens spec sheet from any manufacturer, they're going to be covered in information. There's curves, there's data, there's charts, there's tables containing percentages and numbers and all these crazy things. And each one of those pieces of data that's inside of that spec sheet, they're all there for a purpose, and they're all there to show a specific part about how the lens is going to perform. The curves specifically can be pretty challenging to look at, especially if you don't have a huge background in optics or have studied it for a really, really long time. And we're going to aim here today to break those curves down into a more digestible format. There are three really common types of machine vision curves that we're going to look like, or lens curves that we're going to look at today. First, we're going to look at a resolution curve. This is called an MTF curve. It stands for modulation transfer function, which we'll get into in a minute. Really, this describes how many megapixels a lens can resolve. That's one of the most common questions that comes up is, can a lens resolve a certain number of megapixels? And it's this chart that it describes whether a lens can or cannot do that under certain circumstances. Another really common one is the distortion curve. Distortion curve describes how bent an object is as it's imaged through a lens. If you image a line through a lens, how bent does that image come out on the image plane? And we're also going to talk about relative illumination. This one's a little bit less common than the prior two, but relative illumination describes the lens brightness. How bright is the center of the lens relative to the corner of the lens when you're looking at a particular image? And these can be really important for certain applications, especially when you're doing something like optical character recognition, where you may be needing to truncate certain parts of the image or threshold certain parts based on pixel values. Relative illumination can play a huge impact on that. Each one of these curves describes something very different. We're going to get into each one of them individually. We're going to start with the resolution curve, or the MTF curve. Again, I mentioned the MTF there stands for modulation transfer function. That's kind of a mouthful, and what does that even mean, right? It's a really fancy way of talking about contrast. It's the way us optical engineers say contrast. So when you hear MTF or modulation transfer function, you really should just be thinking about contrast. How white are my whites relative to how black my blacks are, if you were to image these two things side by side. And the MTF curve plots that contrast against a frequency. It plots it against a frequency or a pixel size. A pixel size is really the more practical way to think about that, because in general you're going to be using a lens with a camera that has a finite pixel size. There's a really quick conversion down on the bottom of the slide. If you have a particular pixel size on a camera, you can divide that by 500 or divide that into 500, and you're going to get the frequency that's generally presented on an MTF curve. But I want to break down an individual curve and pick it apart piece by piece to talk about what these things are actually saying and some of the nuances here. We're going to start with what's up at the top. Each MTF curve has a very specific parameter set under which it's run. In this particular case, you generally will run a lens based upon an F number of the lens, so how much light's being let through, the overall aperture of the lens, and at a working distance. You're also going to generally specify it for a specific sensor size as well, and given wavelengths. In this particular example, we're looking at white light, so a composite of different wavelengths. The y-axis is showing that contrast, or that modulation transfer function. And generally speaking, we use about 20% as our limiting value there to say whether or not a lens can or cannot resolve something. When you start getting below that 20% value, you start to get into camera noise and other factors that can diminish the resolving capabilities of the overall system. So 20% is generally a limit for whether we say a lens can or cannot resolve something at a given frequency. That frequency is on that x-axis, and again, as I mentioned on the previous slide, this corresponds directly to a pixel size. You'll notice that there are a couple on this particular chart. We're showing 10 micron pixel sizes and 5 micron pixel sizes. Those correspond to a different individual frequency, and so you'll notice that a 5 micron pixel size would be a 100 line pair per millimeter frequency, or 100 cycles per millimeter for the frequency. A 10 micron pixel corresponds to 50 line pairs per millimeter, or 50 cycles per millimeter. Very quick conversion to get back and forth between those two. The actual curves themselves, there's multiple curves on an MTF chart, and they're all designed to show different parts of the lens. The first thing that I want to pick on is the diffraction limit, or the diff limit one. It's the black line up at the top of the curve. And that curve is defined as the absolute best that a lens can do given its parameters of the F number and the wavelength involved. As you decrease your wavelength and as you decrease your F number, that curve ceiling increases, and you're able to get a better performing lens with those parameters. As it stands, the actual performance curves, which are those blue, green, and red ones, will always be below that black line. It's impossible, given these parameters, to ever go above that black line. In this particular case, we have a whole bunch of different curves on here. We have a blue one, a green one, and a red one. Those blue, green, and red lines each define different positions in the field of view for how a resolution is going to look. The blue line represents what we call on-axis. It's represented here by 0.0 millimeters. We're defining the 0 point in our image as being the center of our image plane. And you'll notice that in this particular case, it's at about 55% contrast. When we go up to green, that's about the bottom middle of the image sensor. So we've gone down to the bottom, and here we see there's two different splits. There's a solid and a dashed line. I'm going to address those in a second. But if we go out to the corner of the image plane, we have 5.5 millimeters. In this particular case, 5.5 is equal to the half diagonal of a 2/3 inch image sensor. The reason why we give the half diagonals, because optics are rotationally symmetric, we like to cut numbers in half quite a bit, because we could show negative 5.5 millimeters, but it would overlay directly on top of the 5.5. So to reduce redundancy, we just cut that out, and we're showing the center as blue, the bottom middle as green, and the corner as red. Now, the other thing I didn't mention yet is those dashed and solid lines. Those define what are called the tangential and sagittal field points. Those are how lenses will resolve different rotational resolutions or different rotational objects as they're put through the imaging lens. And we're going to go into an example from a real-world impact to see what do those actually mean and those different types of resolution that you can get. So we're going to look at something called a star target or a Siemens-Stern target. And this target has an array of different stars on it, and these individual stars have an increasing frequency as you approach the center of those stars. We're going to look at two different 16mm lenses. One of these 16mm lenses was designed to work at machine vision working distances, sort of 300 to 500mm ranges, and the other one was designed to work as more of a CCTV lens. It's designed to be on a street light overlooking a parking lot, picking out cars, things of that nature. So looking at the center, and we're going to look at these lenses side by side, we see that the performances are very similar. There's very little difference between these two lenses here when you go to the center. When you go to the bottom middle, which is representative of that green curve from the MTF on the slide previous, we can see that there starts to become a little bit of a performance difference, but they look still relatively similar. Where you see a huge change is when you go out to the corner of those individual lenses, and you'll see that there's pretty strong differences between these two lenses. And the other thing you'll notice is that if you were to draw an X in between the image on the right, you'll notice that there's some part of that image is really well resolved and other parts of the image are really poorly resolved. That right there is showing the split in that solid and dashed line on the MTF. We're going to advance here to the next slide and bring up what those corner positions looked like to get an idea of how the performance would actually look on a lens. The lens on the left clearly has higher resolution, better megapixel capabilities than the lens that's on the right, and you can see that those splits on the right are driving that performance way down on lens number 2. We can see that there's that red line that's only getting about 30% contrast at 60 line pairs per millimeter. That means it's only 30% contrast at 60 line pairs per millimeter. That means that it's really only able to really properly resolve a pixel size that's around 8 microns. In this particular example, the pixels that we're using on this camera are 3.45 microns in size. So you can see that there are large differences in this particular example between how those lenses perform. Now, one thing I want to make perfectly clear is that I'm not trying to hammer on the fact that lens 2 is a bad lens. In this particular example, we're using a high-resolution camera and we're using a high-resolution target to look at a particular object. And in this particular case, lens 1 would be the better choice. But imagine if you're using a VGA camera that has a 9.9 or a 10 micron pixel in it. Lens 2 would be a less expensive option and would still give you decent performance that you wouldn't necessarily notice if you're just trying to pick out relatively large objects. So looking at the MTF curves in this case, if you're looking at those two spec sheets side by side, is really going to tell you, do I need to spend the extra money on the more expensive lens for where I'm going to be using it based upon my pixel size for my camera? I want to jump into lens distortion as the next part, and lens distortion is one of those terms that we use. It's very specific in optics. From a technical jargon point of view, distortion is magnification variance with field height. Okay, well that's great. What does that mean? Again, it defines how something is bent through a lens. If you were to image a straight line through a lens, how bent is that? And if anyone here is a photographer, lenses that don't have any distortion or have very low distortion, those are often referred to as rectilinear lenses. And if you start to get into more of a fisheye lens, if you've seen a wide-angle lens, a 3.5mm lens or a 4.5mm lens, they tend to have relatively large amounts of distortion when compared to their long focal length partners. Now, I want to get into how to read one of these curves. There's a lot of information on this. Luckily, there's a little bit less. It's a little bit less dense than our MTF curve. Again, we'll start with what's going on our y-axis, and this is as our image height in this particular case. So before on the MTF curve, we represented discrete image heights by the individual curves, and in this particular case, for the distortion curve, we're using an axis for this. So the y-axis is defining that image height, and we've overlaid some common sensor dimensions there. And these sensor dimensions are specifically the corner for those individual sensors. So if you look up at the top, you'll see 2/3 of an inch. That's representative of a 2/3 inch sensor that's being used in this particular case. And we're going from the center, which is all the way down at the bottom of that y-axis, the 0 point, all the way up to the corner of that 2/3 inch sensor. Looking down at the x-axis, that's where we're actually defining what our distortion percentage is. And here we can see it's really important to pay attention to the scale of this axis, as we're going to see in a slide later. The individual curves are defining how much distortion there is for any given wavelength. Generally speaking, there's going to be slight deviations from in amounts of distortion depending on which wavelengths of light that you're using. So just looking at a single number that's often presented on spec sheets for this is how much distortion is in a lens doesn't necessarily tell you the whole picture to be able to properly back that distortion out in something like a software algorithm. Looking at two different distortion curves from two very different lenses, these are a 6mm lens on the left and a 3.5mm lens that's on the right. And the curves themselves look pretty similar. They're both in the same direction, and the magnitudes look the same until you look at that x-axis. You'll notice that the 6mm lens maximally only goes out to about 9% distortion, and the 3.5mm lens goes out to almost 30%. You'll notice these are both in the negative direction. And the other thing I want to point out here is that this is a nonlinear quantity. Distortion doesn't vary in a linear sense, which means that you can't just take a value from the corner and say, okay, I can now scale that linearly down to my center, which I know has 0% distortion. Because these vary non-linearly, we need to have that curve. Sometimes distortion curves can even change sign and go on to the positive side. You can have what's called nonlinear or mustache distortion, or non-monotonic or mustache distortion. And they can present totally different things to a particular sensor. But how does that actually look in a practical sense? Here we're looking at a distortion target that contains several bullseyes, and we're using the 6mm lens here. And the 6mm lens has, again, about minus 9% distortion. That negative percent sign there is to help define what shape the distortion is in. In this particular case, this is called a barrel distortion because it tends to look like the lens image is wrapped around a barrel. And you can see what's going on here is that everything is bent relative to one another, especially as you get out toward the corner. We see that about minus 9% distortion out in the corner. If you look at the 3.5mm lens, again, it has minus 27% distortion, so there's a tremendous more amount of distortion in the 3.5mm lens, and you can really see that evidence there. And looking at the two side by side, you can really see this. There's one other thing that I want to bring up here that's a design trade-off, and that is distortion relative to resolution. When you're doing a lens design, if you have a certain number of elements that you're fixed to and a certain cost that the lens has to hit, generally speaking, you're going to be able to either achieve high resolution or achieve low distortion, and generally not both. If you want to have higher resolution, you generally have to push distortion to higher values as well. And that's one thing to keep in mind if cost is a large constraint for any given lens that you're going to be purchasing, is that you may have to trade off on one of those values. It is possible for lens designers to make high resolution, low distortion lenses. They tend to be more expensive because of the extra materials required and because of the extra design time involved with making a lens like that. The last thing that I want to point out here as a transition to our next thing that we're going to be discussing is look at the 3.5mm lens, and you'll notice the corners are a little bit darker there. This is a concept called relative illumination, or lens brightness, really. And we can define what that lens brightness is using a relative illumination curve. And a relative illumination curve describes the lens brightness from the center out to the corner of the image. And generally speaking, these curves slope from the left side of the plot all the way down to the right. And generally you see that slope. You can see an increase. It is somewhat of a misconception that a relative illumination curve is relative to the center of the lens. That's not always the case. I want to break down how you actually read one of these curves, though. We're going to start here with the f number of the lens that we're using. You'll notice that in this particular case, there's really strong differences between the individual f numbers. At f1.4, again, we're letting a lot of overall light through our system. There tends to be a large drop-off in relative illumination there. And as you increase the f numbers, you go up to f2.8 or f4, we see the relative illumination itself increase. The other thing that this curve doesn't capture is that when you increase the f number, you are decreasing the overall amount of light that's making it through the lens. As you increase that f number, you're getting an overall more uniform image, but it is going to be less light throughput, so the exposure time overall for the camera is going to have to increase. On the x-axis here, we're showing our sensor height. And again, we have several different dashed lines showing common sensor formats. So we have a 1/4 inch, a 1/3 inch, a 1/2 inch, and a 2/3 inch on this particular plot here. And we're showing it out to the corner in this particular case, all the way out to the corner of a 2/3 inch sensor. So we're looking at the center. Again, that 0 point on the x-axis there is indicative of the center of our image, and the 5.5 millimeters is indicative of the corner. How would that actually look, though, from a practical standpoint, is that if we pick on that blue curve, We're seeing we're starting at 100% and we're going down to around 50% relative illumination. And you can see how that would look on the image sensor. You'll notice that it shows that radial symmetry that we're used to seeing because we're using round lenses. And you can also see how much deviation there is from the center to the corner of that image plane. It's important to remember, though, that you are still getting more light throughput overall on the f1.4 lens. And this is another thing to consider when using a lens that's designed for certain sensor sizes. If you're using a 2/3 inch lens, which this lens happens to be, but you're using it on only a 1/3 inch sensor, you can expect to have much higher relative illumination there. Lastly, if you're looking at an object that's primarily located in the center of your image plane, it might not be as important to have a really flat relative illumination curve. If you're doing something like OCR, it might be really important to have that. So again, taking a glance at one of these curves can really tell you what type of performance you're going to be getting in terms of that relative illumination. As one last quick example, showing a couple of images with 100% relative illumination versus 70% relative illumination, you can see that drop off pretty substantially. If you had to do a pixel threshold at some value, you might lose a lot of information in that 70% relative illumination lens that's on the right. You can correct for relative illumination in software. It's something called a field flattening algorithm. And what these do is they adjust the brightness of an individual portion of the image. But what that's going to do is it's going to increase the amount of noise in a system, and it's going to decrease your signal-to-noise ratio. So you're not going to necessarily buy back any additional information there. So it's important to know that if relative illumination is important for your application, look at that curve and make sure that you're going to be getting out what you want so that you know that your image is going to be equally bright across the system or across the field if it's required. There have been a lot of mentions earlier about design trade-offs. I mentioned briefly distortion and resolution. There's another really important one. Lenses generally are designed to work at specific distances really well. I had mentioned factory automation lenses that tend to work well around that 300 to 500 millimeter range. Lenses designed out for infinity. There's lenses designed for all kinds of different parameters. And because of that, lens performance varies wildly over those ranges. And I want to do an example really quickly showing some MTF curves or lens resolution curves, looking at two different 25 millimeter lenses. These 25 millimeter lenses were designed for two different places. One was designed for and optimized for up-close use. It was designed for relatively high magnification inspection. You're looking at fields of view around 40 or 50 millimeters here at working distances of 50 to 200 millimeters. The other lens that we want to look at is optimized between 300 and 500 millimeters. So this is a more traditional factory automation lens. And we want to look at those MTF curves and what you're going to get out of each one if you're trying to use them where they're not necessarily optimized. So we're going to look at these two lenses here. The lens on the right is going to be our high magnification lens. The lens on the left is going to be our factory automation lens, again designed for a longer working distance. And then we're going to look at them in the two different places. We're going to look at them at 300 millimeters, which gives a field of view of about 140 millimeters. And then we're going to look at them at 85 millimeters, giving a field of view of about 40 millimeters. We're going to start with the factory automation lens, which is designed for those longer conjugates. And you can see that we're getting about 40% contrast at 150 line pairs per millimeter. What this means is that this lens is achieving very high resolution at a 5 megapixel image, for a 5 megapixel image. Generally speaking, a common 5 megapixel sensor that's on the market has a 3.45 micron pixel. It corresponds to about 145 line pairs per millimeter, so we're really close to that edge there. And we're getting really high resolution with this particular lens at that 300 millimeters. But note what happens if we try to take that same high resolution lens and use it at an 85 millimeter working distance. The performance drops out and it completely collapses. You'll be spending a certain amount of money on an imaging lens expecting the performance above, but if you try to use it below, you're going to get a lot of differences from what you actually expect. And in this particular case, it would be better to use the high magnification lens. So if we use the high magnification lens where it's designed at the 85 millimeter working distance, we see very similar performance to what we see with the 300 millimeter working distance on the factory automation lens. It's performing really, really well. It's hitting that 5 megapixel resolution really sharply. But if we bring that same lens up to 300 millimeters, we get that performance drop again. And in this particular case, it's not as strong as that factory automation lens's drop, but it is quite tremendous. And you can see how you're down below that 20% contrast value that we generally recommend for where to use an individual lens. So these two curves that I just highlighted are likely what you would find on the spec sheets. And when a lens manufacturer is making a spec sheet, they're going to give you the MTF curve where the lens is designed. And they should be doing that because they want to show this is where this lens is optimized, this is where it's supposed to be used. But note that those curves will vary vastly, and that the curves that are on the bottom, say for the factory automation lens, and the top for the high magnification lens wouldn't necessarily be on the spec sheet. And so it's important to be able to know, you can call your optical supplier and say, hey, I'm thinking about using this lens, and I'm probably going to be using it outside of where I think it's going to be working. Can we just take a look at an MTF curve really quickly? It doesn't take long to generate a custom MTF. It takes a few seconds, and you can get a really strong idea for how a lens is going to perform. So I want to wrap up really quickly. Lenses are really complex, right? We've gone through a lot of different things, and we've just barely skimmed the surface on some of these lens curves and really digging into only a couple of them in great detail. So it can be important to derive a checklist from some of these things. The important things to think about are resolution and distortion, image brightness, and cost. And all of these things will push and pull on one another. I mentioned how high resolution tends to drive higher distortion values. Image brightness can drive larger lenses to allow more light throughput. And all of that is directly contingent on cost as well. If cost is not an object, you can probably check all three of those boxes. If you're more cost constrained for a particular application, you may need to give on one of these in order to get a lens that's going to maximize what you're going to be doing. And lastly, don't hesitate to rely on optical suppliers. You should expect a lot from us. We should know our products and be able to answer any questions that you may have in great detail. Thank you so much, you guys.
Thank you, Nick. Please note we still have a team of expert engineers answering the questions you've submitted in Q&A, and they'll continue to answer your questions after the webinar has concluded. Additionally, we answered many of your questions during the webinar, and there were a few common and notable ones that came up that are worth sharing. So Nick, one question that came up frequently, when looking at an MTF curve, what level of contrast do I need at the spatial frequency I need to resolve?
That's a good question. Generally speaking, we recommend about 20% contrast for a minimum for what we're going to be looking at, and that allows for several different things. That allows for contrast degradation coming from noise in an individual pixel or on a camera sensor. That allows for contrast degradation coming from external factors like light changes or something like that. And so generally speaking, 20% is a solid minimum that we tend to aim for in order to say this lens can definitely achieve that value.
Great, thank you. Another question, how does distortion as a percentage relate to the actual bending of an image?
That's a good question. Distortion is one of those tricky parameters that comes up quite a lot. And really what we're defining is how bent something is relative to where we expect it to be. Let's say you were to use the basic calculations that you would use, say, from part 1 of the webinar, and you'd be expecting certain image heights to fall out. And distortion as a percentage is going to be a deviation from that ideal or predicted position, and that's what that percentage is indicative of.
Great. And can relative illumination be compensated for by adjusting the camera gain?
Relative illumination can be, there are certain cameras that can adjust individual pixel gain. I will hesitate to say that you're going to get any additional information out of this. Again, if you're increasing something like gain, you're not actually producing any more information. It's going to look visually nicer to a human inspector, but you're not actually gaining any contrast. You're not gaining any resolution. So any information that comes from increasing gain individually on a pixel level isn't going to actually buy you any information. It can make some of the software algorithms easier. I had mentioned earlier, I think I had mentioned the flat field algorithms. Those don't necessarily increase gain on the sensor, but that's actual software correction from the image side. But increasing the gain individually can impact the image quality in a negative way as well because of that additional noise that's introduced to the image.
Perfect. Thanks, Nick. So that covers it for part 2 of the webinar. Thank you, everyone. We appreciate you being here. Just a reminder, a link to today's recording will be sent to all participants shortly. You can also reach us via email, the Edmund Optics 1-800 number, or through the live chat feature on our website. Thanks again for joining us today, and we look forward to seeing you next time.